All right, we're back. Oh, weather update for Boone, July 28th, 2020. Kind of a dreary day outside. It's actually our first dreary day in quite a while. Looks like rain this afternoon, so we'll take it. It is a balmy 70 degrees up here. Kind of a little bit sticky. Not at all. Can't wait till y'all are back. Hopefully, we are allowed to come back. This place is just so much better when the energy of the students is here. It's really great. I want to keep talking about some more infrared spectroscopy aspects, some things that I can finally prove to you as well. I hope that you're liking this departure from our normally scheduled reactivity of the day type thing, and starting to learn a little bit more about these techniques that also, I guess I should really say too, this is certainly being told as chemistry, but let's give respect where respect is due. A lot of physicists have been integral in the development of this type of technology as well. This is just some really neat stuff. I want to be able to just talk about the shape of these types of things, and I also want to be able to peaks by that. I also want to be able to talk about just an artifact that we can kind of start to prove that different bonds have different types of energies as well. So when we're looking at IR, so a peak. If we're looking and saying when we have an IR spectrum, what gives rise to the presence of a peak, period. And so that's what I'm going to start with. What gives rise to the peak being there? Well, a peak presence is determined by a bond in the molecule. Okay, if the bond at the correct energy does not exist, it will not demonstrate or display a peak in the spectrum. And so we're looking at, when you're looking at like propanol, this region right in here. All right, its intensity is determined by how well the light is absorbed. And by that I mean, how efficient is that molecule at absorbing that light is what I'm saying there. And then the shape of the peak, that is determined by the number of like bonds in the molecule. Okay, and that's something I'm going to dive into in just a second. And then the position of the peak is determined by differences in bond strength and length. And so when we're looking at the IR, I want to be able to make sure you understand, why do I see a peak and why do I see where it is in the shape that it is. This is giving rise to, if you know everything about the instrument that I just told you, this is what dictates the overall shape and position and blah, 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 or the presence or appearance. I did it again. I got to stop pointing to the screen for you guys to see something. That gives rise to the spectrum here. I don't think I'm ever going to be able to stop that. But yeah, use the mouse, stupid. And that gives rise to that right there. I want to just go into a little bit more of a discussion on shape. Why is this peak right here really sharp? Or let's look at this. Okay, so here's acetone, fingernail polish remover. Why is this peak really, really sharp? And why is this peak really, really broad right here? And so shape, let's just take a quick little detour into shape. When I say the shape, broad peaks, lots of like bonds, and sharp peaks are equal to only one type. And what I mean by that is, if we were to compare an OH stretch to a C double bond O stretch, then when we look at our IR spectrum, how come that CO stretch is sharp, and how come the OH stretch is broad like that? And the reason why is really simple. There's only one type of bond at that point in a carbonyl that can only do one type of movement, a stretch like that. And if there's one bond with one movement, it's one energy. How I ended up holding up three fingers, I don't know. But it's one energy that excites that bond, and it's going to make the molecule do one thing. And at that point, you're going to get one sharp peak to denote, hey, only one molecular motion is occurring. Well, when we look at an OH stretch, then, what's occurring here is the stretch of this oxygen moving away from this hydrogen. And so that's what's occurring right here at this position. So we'll just say 1 right there. But in an OH bond, this proton is actually acidic. And so it could dissociate in solution, and maybe that peak would appear. Let's take a look at position number 2 right here. Maybe that proton has started to dissociate a little bit further away from that oxygen because it is in fact acidic. We're still seeing the same stretch that occurs, but because this distance is slightly different, then it's going to appear at a different peak position because that bond is slightly longer. And you could apply that then to this position here as well, number 3, letter number 3. Perhaps then at this position, that oxygen has said, no, we're really going to hold on to that proton. And so this distance is a lot smaller. And as a result, this stretch requires a different amount of energy. It's still the same OH bond, but it requires a different amount of energy in order to accomplish that stretch. And when it does, because that distance is different, it's a different energy, and it appears at a different position. But it's a position that is still very close to the position of other like bonds. And that's what gives rise to a set amount of different, the shape of this peak is really what I'm kind of envisioning here in my mind, is that this is kind of the, how do I do this? It's kind of like the cumulative sum of all of these peaks put together, like this, and adding all the ones in between it. You're just seeing a whole concert of bonds that are all very similar to one another. And that's what gives rise to those broad peaks, is really having a union of this. So OH stretch in a liquid, we would expect a concert of peaks. This same thing, let me just write this. I can do that right here. If we were to see an OH stretch of a solid, you would expect to see one sharp peak at 3400-ish, because you are packed into a crystalline solid. All of these OH bonds are set to the exact same distance. All of those OH bonds will be excited at the same wavelength of light, and boom, they're all going to appear in one sharp, beautiful peak at 3400. If you let that solid start to melt, you get a larger diversity of OH bond lengths as a result, because that's a liquid now, and now all of a sudden you're going to see a broadening of that peak to distribute over a larger region. And if you were to add up 100 different peaks, all at different values, you get this really large looking peak. The other thing I just want to briefly talk about before we get into mass spectrometry is the position. So we did just a little bit more on shape. Let's talk a little bit more on position. And what I want to do here is just compare this. And then I also want to compare I want to look at the carbonyl. So we're going to be looking at the carbonyl position in each and every single one of these different types of arrangements of carbonyls, either in our ester, our conjugated ester, and then our amide. And for us, when we look at these different types of bonds, let's take a look at where we would anticipate seeing those types of bonds in our IR spectrum. And so we're going to go up here. Examinations, I'm working on them as fast as I can. It's been a roller coaster here. Not only did we kind of lose a family member, we also gained one, apparently. My sister got engaged. And so it's kind of been this big roller coaster of emotions, and very happy, but just the exams are getting graded today, and I'll get those numbers out to you right away. I personally feel horrible the second I can't get those examinations back to you the next day. You're required to take the examination on a day, and it should be required of me to return those in a day. And I didn't meet that, but I appreciate your patience and understanding. I'll have those grades out to you today. But what I'm looking at here is saying, here, hey, that's pretty wild. An ester is going to appear at 1735 inverse centimeters. And you're looking right here, okay? And then this data right here, it's not in our table, but what I want to show you is that we would expect to see this conjugated one appear at 1710 inverse centimeters. Interesting. And then we would appear that an amide would appear way down at 1640 inverse centimeters. And so I guess what I'm asking is, if we're looking at the carbonyl center, that's what I was writing. If you're looking at the carbonyl center of this molecule, I was telling you a carbonyl should, have one stretch that should appear at the same place. And so if in fact the position of the carbonyl portion of our esters or amides are appearing at different positions, 1735, 1710, 1640, then the sub-question becomes, what is the influence of the stuff that is attached on this carbonyl such that it would cause that carbonyl to appear at a place where we weren't necessarily anticipating it to appear initially? So I've got this ester over here with this OR portion, and that's appearing at 1735. I wonder what the impact of this could be. Okay, I've got this amide over here. So let me first compare the conjugated ester to the ester and see if we can come up with the reason why we would expect this to appear at a different position, and then we can deduce together what that common understanding is. Well, let's see. A conjugated ester could be drawn as a resonance structure wherein the oxygen has that negative charge on it. We have a positive charge on the terminal carbon. And now we've got that alkene in between this carbon and this carbon instead. We're just drawing a resonance structure. Well, in this resonance structure, and this is just so freaking cool. This carbonyl sometimes is a single bond. Sometimes it's a double bond. Well, if some of the time that carbonyl is a single bond, it's going to be longer. And what we're deducing is that the more single bond characteristic, the longer the bond and a shift to lower wave numbers is observed. Well, I know that we just kind of came up with a rule based on observations that we found. Here's a C double bond O, and then here's a C double bond O that could exist sometimes as just a C single bond O. And that difference results in a different length in bond. This distance here is going to be a little bit bigger than this distance here. We'll write d tiny d normal. Longer. I know this is real scientific, but because that bond is a little bit longer, it's going to absorb a different energy, and the correlation is that that energy should be a wave number that is shifted to a lower wave number to excite that bond. And so, okay, great. I have this rule that is now explained. Awesome. But what does that actually prove? It freaking proves the existence of resonance. Absolutely. We have a spectroscopic method that proves a topic that I taught you in OChem 1 or Ramey taught you in OChem 1, resonance. We've always said you can move electrons around a pi bond and they exist in different extremes in representation. And y'all probably were nodding, yes, this makes sense. Prove it to me. Well, here's the proof. Those bonds appear at a different position because they are of a different type of intensity, not intensity, but a different length, and that requires a different wave number. And so to excite that bond. And as a result, hey, that's pretty cool. We would actually expect it to have a different wavelength of light it would absorb, thus proving that this is a very dynamic bond once conjugated, and that the atom is slightly different when conjugated than right here. So sub-question becomes then, what does that infer about the actual state of an amide instead? If the wave number, this is, I've been teaching this crap for 12 years now, and I still get excited about this. I just proved to you that conjugation actually freaking exists with just infrared spectroscopy. And then take a look at that. This is some amount of math, 35 minus 10, which should be, 25 wave numbers. I'm saying that resonance is going to change the bond to be a little bit more single bond characteristic like, and as a result, it's going to see a shift in 25 wave numbers. Holy crap, 100 wave numbers to switch between an amide and an ester. What does that suggest about the amide? Well, that suggests about the amide I was bringing it home so well, and now it just looks so ugly. Let me just pause and time out, look away, look back. If that shift in wave numbers is actually true, which it is, then that suggests that this is the dominant species. When you have an amide, that nitrogen is more likely double bonded to the carbon. It is more times than not that carbon-oxygen bond has more single characteristic than even a conjugated system. So in an amide, if you were to take open your eyes, close your eyes, open your eyes, 9 times out of 10, you're going to see the resonance form that is this over this, because you see a huge shift in wave numbers that excite that carbonyl way down at 1640, which suggests that this carbonyl does not have the double bond characteristic as much as this, or even as much as this. And it's so much pronounced because the wave number is pushed so far down that suggests that this molecule actually exists more like this than it does like this, which is truly, truly, truly fascinating. And as a result, we would expect this species to be the more dominant resonance structure when looking at amides. Its dominant exists more in solution than you would anticipate. Let me just take a look at one more thing, and then we'll move to mass spectrometry, because in all honesty, I could do this for another hour and a half talking about how cool this stuff is. It's proof to stuff we've been telling you for a long time. Let's compare one other thing, which would be an aldehyde or ketone. To this ester. An aldehyde or ketone, we'll say this is a ketone right here. We would expect a ketone to appear at 1710 as well. Over in ester, yeah. So why is this then so much further ahead of this ketone right here? Why would we expect that ketone to absorb at 1710, which is similar to this conjugated one over here, versus the ester appearing at 1735? Because the ester appears at 1735, we would expect, so when we compare these two things, let me do this in a manner that would make sense. When comparing these two right here, it's suggesting that the ester, which is at 1735, is stronger with more double bond characteristic to it. How is that true? I'm going to draw this just a little bit more a little bit more explicit. This oxygen is electron withdrawing. In a way, it's going to pull electron density through the sigma bond. You might be thinking in a pi bond it donates. It does, but in a sigma bond, and this bond right here, oxygen is electronegative. It's going to pull electron density towards it, and that will subsequently shorten this bond, making it smaller, making it stronger, and requiring a different energy that is higher in order to make that oxygen carbon bond start to stretch. And so you can see that that these differences aren't just differences based on the presence of atoms, but differences that are imparted structurally by the presence of those atoms. There is a reason why this stuff exists as it does, because those neighboring atoms impart massive changes to the molecule. And look at this stuff, people. Think about it. Think deeper into it. These molecules are absolutely dynamic, and we have a way of measuring just micron changes, angstrom changes of distances between atoms using IR light. And we've learned how to decipher the data to give us a lot of information about about its structure and minute changes in its structure. And if that doesn't get you excited enough, there's one of these instruments on a goddamn different planet. A totally different planet has two of these instruments on it, and it's functional, and they have come back and told us that there is frozen water on Mars using these instruments. That is absolutely fascinating. That is a absolutely cool aspect of human development. And not only that, look at what else is on the SAM instrument suite. Find it. Where is it? Mass spectrometer. There is a freaking mass spectrometer on this thing. So let's talk about what's on this rover, that mass spectrometer. Look at that guy. He probably worked so hard to get to where he is to be able to be the lead principal investigator on a robot on Mars. That is so cool. Good for that guy. Mass spectrometry, people. Because we are not using wavelengths of light in mass spectrometry, then the mass spectrometry portion, we're not using spectroscopy, we're using spectrometry. Let's just, I want to show you these things. Let's see if we can find another Asian guy with a mass spectrometer. Let's just look up the classic one, GCMS. So here's a GCMS. This is actually really close to the instruments that we have in the laboratory right now. You can see, we'll work through this schematic. Sorry, clicking a lot real fast here. That's the instrument. It looks about the size of a microwave, a little larger than that. I think some of you, if you took OChem 1 lab when we were still having it in person, have seen this instrument. Inside of this is the mass spectrometer. Here's, oh, look at that one. That's just gorgeous. Auto sampler attached here to a mass spectrometer. If you like any sort of procedural on TV, NCIS, CSI, in the background, they typically have mass spectrometers that they, you see them put in a sample and it spits it out, 1974, blue Ford. They can actually do that now, and I'll talk more about that. It's pretty cool stuff. Let's look at shopping. $20,000 ish for a mass spectrometer. There's a lot of different types of mass spectrometers out there. This one's worth $80,000. Yeah. Here's another one that's about $27,000 for one of these instruments. You would not want to drop this 1 centimeter on a benchtop. There's one right here. Certainly some really cool instruments. I currently have my own business that I'm starting with private investors, and they asked me what I wanted in my own lab. They're building me my own state-of-the-art laboratory, and so I just told them I wanted one of these right here. I don't even know how to use it, but we're gonna buy one anyways. We're gonna need it, but yeah, be aware so that exists right there. Let's talk about what a mass spectrum is and how it works. Mass spectrometry is going to ultimately give us our charge to mass ratio, and that is really for our practical purposes here, because we aren't dealing with macromolecules. That can be considered its charge to mass ratio, right? And let's say you like in your spare time some recreational substances of the green variety of the plant type. Certainly, you probably have someone that affords you that, or if we were in Colorado, you'd go and you'd have them pick out some from a jar with some tweezers and put it on a scale, and they're going to measure down to the gram. and dispense accordingly. But at some point in time, if there's just one little leaf there, they're probably not going to worry too much about how much that adds to the overall weight, and I guess today people are dealing in metric for their recreational drugs. I don't know when that transition happened. Back in my day, it was more about the English system of eighths and ounces, if you had enough money for one of those. But the idea being that there is some point in time where the mass no longer becomes measurable. If you're trying to get an eighth of some really, really good sativa, at that point in time, there's some point, rather, in time where the weight of what you're weighing just doesn't really matter to the overall $60 that you're going to shell out for that fun time. Certainly more safe than $60 of Jameson, that is for sure. But if you think of that example, there's a point when just the weight just becomes negligible. I'm going to tell you that we can weigh one and only one molecule. And if that's the case, how did we get to a point where we're that accurate? How can you accurately weigh just one and only one molecule? And that's really what I want to be able to explain to you and be able to take a look at. So let's look at how a mass spectrometer, how it works. And for this, we will be using, for this example, we will be using what would be gas phase mass spectrometry. You can do this in a solid phase. You can do this in a nebulized phase. They're called electrospray ionization. Those instruments are $200,000 a piece. They could be done in the solid form, which is called matrix-assisted laser deionization. That's my favorite method of this. That's just done in the solid phase. I ordered one of those for my business. It's $100,000. Really excited to get one of those. But there's different methods of mass. What I'll be demoing in this portion is the gas phase version of mass spectrometry. Well, what happens? You've got something that is going to heat the sample, and that is preceded by an injector. And so what we're simply suggesting here is that you have some type of sample that gets injected into the injector as a liquid or dissolved in a liquid, and it hits this heater and essentially starts coming out of here as a gas. And so that's all we've essentially done, is we've converted something to its dissolved in a liquid or in its liquid form, and then heated it to a really high temperature to convert everything into a gas. Once that sample has gone through this, and so what I want to suggest is we'll just call the sample the molecule with an M. And so at this point in time, and let me do this in another color so we can keep track of this. But the molecule itself, we want to be able to record kind of what's happening as this molecule changes. And so we'll just say M for the molecule here. So that means the molecule was a liquid right here. And then the molecule is now a gas right here. So I want to be able to keep track of the state and appearance of this molecule. Well, after that point, after it's been turned into a gas, it is bombarded by an electron beam, which is high energy. Sorry, the handwriting is starting to go, and apparently the spelling as well. But you get the idea that this beam of light is really coming through, and our sample must encounter that high beam of electrical energy at some point in time. Well, what happens then is that at this point, this is at an energy where the weakest bond will break. And in fact, all bonds will break. So we'll say weakest and all. But what I'm going to be doing is tracking tracking just the weakest bond when we look at this, but you're envisioning just like really something out of Star Wars when Star Wars was good, or Star Trek when Star Trek was good. But the idea of you're blasting something with like a laser beam, and that has a high enough energy to really start to shatter that molecule, and it will absolutely fragment the molecule. And depending upon how high of a current you apply to this electrical beam, you can be more precise and more selective in what types of bonds are going to explode. But if you're someone like me, you just blow the whole thing up. But the idea is that once this happens, you form your molecule that now is a free radical. So maybe a carbon-hydrogen bond exploded, and as a result, you lost a hydrogen, and you now have a molecule that has a charge on it. And so typically people will see this as an M dot plus or an M plus dot, is what the molecule now is. Once that happens, the molecules then, which are now charged, encounter magnets. And these magnets are tuned and can be tuned such that because this molecule possesses a charge, that charge is then going to be deflected by that that path of magnets, and its path of flight, which was going to be straight, now becomes deflected based on its charge and how much mass that charge has. And so a molecule that might be larger with one charge on it encounters this magnet, and because it's larger, gets deflected less. Maybe it's a really small molecule with some type of charge on it. And because it encounters this magnet and it's small, that magnet will pull it really close because it has less mass. What that gives us then is a deflection in its path, to which then these molecules start to hit a detector. It's like Battleship. That's a hit. And when it hits that detector, keep in mind that your instrument now has a reference point of where non-charged molecules should appear and where your molecule appears. This angle right here is what's measured by the instrument. And that angle can then be back calculated. The angle of deflection is directly proportional to its charge to mass. And so where it hits on this, maybe it's deflected to here, maybe it's deflected to tiny little bit here. We know the measurement based on how much that should have been deflected and its mass. And so this then enters a computer, and out of that comes our mass spectrum, where we start to see peaks with respect to its mass to charge ratio and the relative amount. And so that each and every single one of these peaks represents a fragment of our molecule that has exploded when it hit this electron beam. Different pieces of that molecule got deflected to different areas on our detector, and then we back calculate based on its angle of deflection what its mass should have been, and we can calculate for each and every single one of these peaks a different charge to mass ratio. So let's give this an example now. If we had ethanol, then we would have ethanol as a liquid. When it first encounters that heat source, then it gets changed into ethanol as a gas. And in the back of your head, you're still thinking to yourself, holy crap, there's one of these on Mars. Angle of deflection, very tiny, right? Molecules, very, 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 very small. So differences between a CH3 and a CH2CH3 are going to be very small. How that landed on Mars and didn't get destroyed and still is able to calculate, nanometer differences, fascinating. Once it hits this electron beam, we start to produce fragments of ETO dot plus, like that. So we just lost the hydrogen and gained one of those electrons. Maybe we have the CH3, CH2 portion, and now we have the corresponding OH dot with this plus on it over here, and maybe we get another fragment that blows the heck up, which is a CH2, CH2OH, where this part has a dot over here with the plus sign, and we'd also be getting a H dot with the plus sign over here. That molecule can explode, and it can explode at any single bond in that molecule. So I'm just trying to capture a few different types of molecules that could be observed in this type of explosive property. And what I'll suggest here then is highlighting just the different path that these, we'll just say this one right here would take versus something like this would take versus the path that something like this would take. Hopefully you're kind of seeing decreasing size here. But as these molecules then travel past these beams, or these magnets rather, what you're seeing here is this, this ethanol without the proton portion of it. Because that's so big, it maybe doesn't get deflected too much because it's really large. The OH is a little smaller, so the impact of that magnet becomes a little more pronounced. This becomes even more pronounced because it's the smallest piece, so that magnet's going to have a really strong pull on it right away. And when it hits this detector here, where these things hit, how far away they are from where we would have anticipated them impacting the detector, this difference we can back calculate to its angle, and once we back calculate to its angle, we can then know something about the weight that would have been required to deflect in this manner. And when we start to get our spectrum that occurs, because there's a bunch of different peaks, you would expect to see this peak maybe way out here, maybe this peak right in here, and because it's just a hydrogen, we would expect this right here. That's where we would see peaks occur in our mass spectrum. So some important aspects here. Every peak is a fragment. Everything here is quantifiable. This axis right here, the relative percentage, that's quantifiable. So that what I'm saying here is if this peak is larger than this peak right here, that means we had more pieces like this than we did like this. We had more pieces that appeared here than we did here. And if this is twice as high as this, we had twice as many peaks or molecules that blew up this way than we did molecules that blew up this way. Okay? And so every peak is absolutely some molecule fragment that occurs. Other important aspects about this. The peak that is farthest right is called the M plus peak, or M plus dot peak, and that is the one that is most likely the molecular weight of your molecule. Okay, and so if this 12, 24, 30, 46, 47, 46 M over Z, that would be what we would expect for, I think, ethanol, if I did all that math correct. 12 in my head, perhaps not at all. Maybe it's worse, I don't know. But you get the idea. Maybe that's the molecule's molecular weight. There's also the tallest peak. Is called the base peak. And that is the most stable. Blowing up piece. I know that's not very scientific, but it's the most stable fragment that we would expect to see. And so this is your M plus dot peak. That should be your molecular weight. This right here is our base peak. And that just happens to be the most stable peak. And then the last little artifact that I'll show you here is that this should be a piece that fell off. So maybe this is the CH2O peak, and then maybe this is like the same thing of the difference here of maybe a CH2OH over here has fallen off to get to this point right here. And we'll get more into that. This molecule can absolutely fragment, and those sizes have different, the magnets impact the size of those molecules differently. It deflects them differently and gives rise to the appearance of peaks at different positions based on what blew up and how it was impacted by that magnet. And so when we look then at what we would expect to see here. Hey, I did get ethanol correct. Here's the mass spectrum of ethanol. And ethanol weighs, in accounting for all of its isotopes, 46.06844 grams per mole. That's not quantifiable because that's the whole, a mole of these, how much it would be. So any one individual molecule should weigh 46-ish grams per mole if it is isotope free. And as a result, we would expect to see a peak right out here at 46 M over Z, or grams per mole. We also see a peak here at 45 M over Z, or grams per mole molecular weight. What the heck could that be? I wonder if that is the stability of this without that proton on it. Perhaps, or I'm sorry, a different one of these broken off with a proton on it. And then here's getting to that base peak. So perhaps since that's at 31 grams per mole, we're looking here at 12 for that carbon, 24, 5, 6, 7, 8, 29. So maybe some fragment here of this ethyl group, but not necessarily. Perhaps some weight of maybe you'd have to weigh up the different portions of this molecule to try and find what that fragment, most stable fragment, could be. And we'll come back and look at that in more depth when we get back together tomorrow. But what I simply want to show you is, look, we're correlating the molecular weight of the molecule to the peak that's furthest to the right, 86 over here. So what's that little peak right here? If every single peak in a mass spectrum is something that has a weight to it, what could that possibly be? It's likely our molecule with one deuterium on it instead of a hydrogen. A deuterium has one more neutron in it. It's going to weigh one more molecular weight unit than its non-deuterated form. In its non-isotopic form, and when it does, it is going to weigh just a little bit more. We're going to come back and talk about how we can use mass spectrometry to identify some key portions of molecules moving forward when we get back together tomorrow. With that being said, check out those lectures on the derivatives of carboxylic acids. We will talk about those a little bit either tomorrow or the next day. Have an enjoyable Tuesday, and I will see you again tomorrow morning.